All right, guys. So in this one, we're going to talk about approximating a definite integral using Riemann sums. Now, a couple things here. On the AP exam, Riemann sums that are formed using the left endpoint are called left Riemann sums, and sometimes they'll be talked about by left rectangular approximation method. Riemann sums formed using the midpoint are called midpoint Riemann sums or midpoint sums, and that sometimes they're referred to as the midpoint rectangular approximation method. And then you also have same thing with the right Riemann sum. So we're going to approximate the definite integral from 1 to 9 of x minus 3 quantity squared by partitioning 1 to 9 into four subintervals, each of width 2, and then we're going to do the left, right, and midpoint rule for those ones there. So for in this particular situation, each of them have a width of 2, so delta x is going to be b minus a over n. So which is 8 over 2, which is 2. So the four subintervals would go from, you start at 1, so you go from 1 to 3, 3 to 5, 5 to 7, and 7 to 9. Those are going to be our four subintervals. So for part A, if we're going to do a left Riemann sum using proper notation, the integral from 1 to 9 of x minus 3 squared dx is approximately equal to the sum I equals 1 to 4 of f of ui delta x. Okay, so the first, notice we're going from 1 to 9. The first subinterval goes from 1 to 3, so its width is 2, but I'm going to use the left endpoint to designate the height. So that's going to be f of 1 times 2. So it's this right here. Plus, the next subinterval goes from 3 to 5. So I would do f of 3 times 2 again. Plus the next interval, 5 to 7. So we do f of 5 times 2. And then the last one is going to be f of 7 times 2. So the rectangle that goes from 3 to 5 using the left endpoints would have no height. From 5, it would be like this, and from 7, it would be like this. So you can see we're going to under approximate. Notice all of them have a uniform width of 2, so we could factor out a 2 and then get the function values. F of 1 is 4, f of 3 is 0, f of 5 is 4, and those should actually be pluses. And then f of 7 is 16, and multiply these together to get 48. Okay, now for part B, if we choose the ui to be the right endpoint, then similarly, we're going to have this integral from 1 to 9 of x minus 3 squared dx equals the sum I equals 1 to 4 of f of ui delta x. But here we're going to use the right endpoints. So the first subinterval goes from 1 to 3, and the right endpoint of that first subinterval is at 3. So we're going to do f of 3 times 2. Then the next subinterval goes 3 to 5, so the right endpoint would be f of 5 times 2, then f of 7 times 2, then f of 9 times 2. Okay. In this case, the right endpoint is going to yield different rectangles. So the first rectangle is going to have a height of 0. The second rectangle is going to be there. The third rectangle is there. And the last rectangle is going to stick out over like that. Again, all of them are multiplied by 2, so we could factor out a 2 and then get the function values. F of 3 is 0. F of 5 is 4. F of 7 is 16. And then we have f of 9, which is 36. Multiply all those by 2, and you get, or add them up, multiply by 2, and you get 112. And finally, for the midpoint, you're going to do the same type of deal here, but the function values are going to be different. For the midpoints, if the first subinterval goes from 1 to 3, the midpoint is going to be 2. So f of 2 times 2. Plus the next subinterval goes from 3 to 5. The midpoint is 4, so f of 4 times 2. Then f of 6 times 2. Then f of 8 times 2. So just want to show this to you here. If I'm going from 1 to 9 and I'm going every 2 units, the midpoint of the first one is at 2, I would use that as the height. Then at 4, that is the height. Then at 6, I'm going to use that as the height. And then at 8, I'm going to use that as the height. So that's what the rectangles would look like for that one there. So here we're going to have f of 2 is 1, f of 4 is 1, f of 6 is 9, f of 8 is 25. We can multiply all those by 2 and get 72 for that one there. Okay, so depending on the behavior of the function, it may be we may be possible to determine whether an approximation is an underestimate or an overestimate of the true value of the definite integral. So here we have a couple hypothetical scenarios. A function is continuous on a closed interval -3 to 8 and is differentiable on the open interval -3 to 8. Suppose f prime is positive between -3 and 5. So sometimes it's helpful to just like draw some of this. 1, 2, 3, 4, 5, 6, 7, 8. Here's 8. Go from -3 to 1, 2, 3, 5, then 5 to 6, and then 6 to 8. So I know f prime is positive for -3 to 5. So f is increasing, and then it decreases, or no, it's constant, and then it decreases on that last interval. So for each integral, we can determine whether a left Riemann sum overestimates the integral, underestimates it, or there is insufficient information to draw a conclusion. So from -5 to 3, or excuse me, -3 to 5, okay? If the derivative is positive, that means the function is increasing, whether it's increasing in a concave down or concave up or linear manner. If I choose if I choose a subinterval, any size, but on that interval somewhere, and I take the left endpoint, no matter where I pick it, the rectangle's going to go underneath the graph, so it's going to underestimate. From 4 to 6, the function is increasing. Okay, so we're going from 4 to 6. So the function is increasing on the interval 4 to 5, and then constant on the interval 5 to 6. So increasing and then constant. So if I go 4 to 6, here's 5. So we go increasing and then constant. So the value of f at the left endpoint is going to be less than or equal to that of f at any other number in the interval. So the Riemann sum is going to underestimate in this case. So constant is going to not increase or decrease. It's going to remain constant. So it's going to like level off. And then before that, from 4 to 5, the derivative was positive, and it could either be concave up, concave down, or simply linear. And a left Riemann sum is going to underestimate the value on that interval from 4 to 5, and then from 5 to 6, it's going to be constant. Okay, and then for part C, okay, the function is increasing again on the interval. So if we're going from 4 to 8, okay, so from 4 to 8, we know that on the interval 4 to 5, the function is constant. Okay, or excuse me, it's going to be on the interval 4 to 5, it's increasing. And then it's constant on the interval 5 to 6. And then on the interval 6 to 8, it's decreasing. So we can't actually draw a conclusion about the relationship between the left Riemann sum and an arbitrary Riemann sum. So it's impossible to determine whether it would overestimate or underestimate. So in general, there's some particular patterns. A function f is continuous and increasing on the interval a to b. A left Riemann sum is going to underestimate, a right Riemann sum is going to overestimate. And if a function is decreasing, the reverse is true. A left Riemann sum overestimates and a right Riemann sum underestimates. So, I mean, you don't have to memorize that, just kind of think about it and draw a picture. So if a function is decreasing, okay, it's either going to decrease in a concave down, a concave up, or a linear manner. Okay, if I pick a subinterval and I choose the left endpoint, okay, no matter where I pick it on that interval, if I draw the rectangle, they're all going to overestimate the value of the definite integral on that interval for a left endpoint because the rectangle is going to stick out over top of it. Okay, so it overestimates. Had I used the right endpoint, well, then my rectangles would underestimate. And then you can draw a function that's increasing in concave down, increasing in concave up, or just linearly increasing. Pick an interval, pick the left endpoint, and you can see that the left endpoint is going to under approximate it. And the reverse would be true for the right endpoint. Okie doke. All right, guys, that's it for this one. I hope that was helpful to you as well. Take care now.